to the next lecture 9, continuing with the carburetor and injection systems. So the next topic as per your syllabus is calculating the AFR, the air fuel ratio. We've already explained to you what is stoichiometric in the previous lectures. Now, once again, stoichiometric means chemically correct. And so, stoichiometric AFR is defined as the ratio which provides sufficient mass of oxygen for complete combustion of a given mass of fuel. So, stoichiometric mixture means the complete mass of fuel which is injected is completely burnt, and for that the right amount of air has to be supplied. That is called the stoichiometric AFR. Now the topic is calculating the AFR. It's very simple, very simple calculation. I'll read it. Most fuels we use in IC engines are hydrocarbons. We all know that. Fossil fuels. And their burning will result in the release of hydrogens and carbon. Hydrocarbon means hydrogen and carbon as residuals along with heat and pressure. Self-explanatory. Example, now we are going to take one example. Example of oxidation reaction of methane, natural gas. It's come in the market, vehicles are running on natural gas as a fuel. So here, methane is CH4 plus, let us see the reaction, plus 2 oxygen molecules result in CO2 plus 2 H2O. This is the chemical reaction when we burn CH4 with oxygen. Now let's calculate the AFR of methane. If we look at the atomic weights of the atoms that make up octane and oxygen, we get the following numbers. This we studied in class 9, 10 in school. We get the atomic weights. We know that the atomic weight of carbon is 12.01. We studied in school, as I said. Oxygen is 16 and hydrogen is 1.008. We have also studied in first semester in your college. So, one molecule of methane has a molecular weight of CH4. Carbon is 1 into molecular weight of atomic weight of carbon plus H4, 4 into 1.008 hydrogen, that is 16.042. So the molecular weight of one molecule of methane is 16.042. One oxygen molecule weighs O2, this O2, 2 into 16. 2 into 16, 32. The oxygen fuel mass ratio is then 2 into 32 divided by 1 into 16.042. 2 into 32, this is this 2. 64 divided by 16.042, that is equal to 3.99. So oxygen fuel mass ratio is 3.99. We know all this. What does this mean? This means that we need 3.99 kg of oxygen for every 1 kg of fuel. Very simple. We need 3.99 kg of oxygen for every 1 kg of fuel. But how much oxygen is there in the atmosphere? Mass-wise, it is only 23.2. The rest is, we know, is nitrogen. 76-77% is very small. Other gases are comprised very small. We know that the atmosphere has 23.2 mass percent of air is actually oxygen out of the air. So considering that, we need 3.99 into 100 upon 23.2, which is equal to 17.2 kg air, 3.99 kg oxygen and 17.2 kg air. Out of this, 3.99 will be oxygen and the rest will be other whatever the components of air are for every 1 kg of methane. So the stoichiometric AFR of methane is 17.2. 17.2 kg is the air required for burning 1 molecule of methane. So the AFR, stoichiometric AFR, is 17.2:1. So what does this mean? When the composition of a fuel is known, when we know the chemical composition of a fuel, this method can be used to derive the stoichiometric AFR for the most common fuels. As a homework, I've done for methane, do it for petrol and oxygen because you know the values, I'm intimating them. It's very simple. Do it. You know the atomic weights. Take out the chemical formula of petrol and diesel and work it out. You will come to the figure of 14.6 and 14.7. Try it out. Now, what are the stoichiometric AFRs for various fuels which are in use in automobiles today, which we are using on the roads? Natural gas, 17.2, we've just worked out. Gasoline means petrol, it is 14.7. Propane, it is 15.5. Ethanol, these are the alcohols. Ethanol is 9. Alcohol, not this. Alcohols are ethanol and methanol. Propane is different. I think this is we use in our kitchens. Ethanol 9, methanol 6.4. Hydrogen 34. Diesel 14.6. 14.6 is diesel. Petrol is 14.7. Now, this is a very interesting point emerges here. Interesting to note that methanol and ethanol have low these are both alcohols, have low AFR, 17.9 and 6.4, while the carbon chain length is comparable to methane and ethane. The carbon chains are comparable, almost the same length of carbon chain. The reason for the low AFR is that alcohol already carries oxygen themselves, which reduces the need for oxygen from the air. They already carry oxygen in their molecular structure, so the requirement of oxygen from the air reduces, and that is why their AFR is low. So this is the procedure of calculating the AFR. As I said, very simple. You must know the chemical composition of a fuel and atomic weights you know, and just calculate it this way. You can get it for any fuel. At least now do it for petrol and diesel. The next now topic is, we come to injection systems in IC engines. The next topic as per your syllabus, Unit 2, is injection systems in internal combustion engines. Let us first see developments in petrol engine And next lecture we will see about the diesel engines. This is short because time is less. There is a governing of fuel carburetor are some of the developments. There is a governor which is placed between the carburetor and inlet manifold to govern the amount of fuel which is to be injected into the engine. The types are vacuum type and centrifugal type. What happens in the vacuum type? The vacuum type depends on the pressure of the moving fuel air mixture at a particular set value by the manufacturer. The air fuel mixture not permitted to enter the engine at a faster rate. It controls the rate of entry. The vacuum type controls the rate of entry of the mixture, fuel air mixture. Centrifugal type, as the name suggests, this is attached to the camshaft, overhead camshaft, which operates the inlet and outlet valves. Inlet valve we are more concerned here for the inflow of fuel air into the cylinder. Weight attached to the pivot arm of the governor. Pivot arm of the governor used to control flow of petrol into carburetor. There must be a valve below which opens and closes, and that controls the flow of petrol into the carburetor. Hence, once you control the flow of petrol, you automatically control the engine speed. So, now we come to the ECM. Electronic control module. This is replaced the carburetor, and you find the carburetor in very few vehicles. In fact, stationary engines in agriculture, marine use, like that. But on the road, we rarely find the carburetor. Time is gone. It was there in my time, but no longer. ECM is called the 18, 16 or 32-bit computers. It replaces the carburetor by injecting fuel directly into the engine. Carburetor indirectly to the manifold. Here it directly into the engine cylinder. In diesel engines, the fuel is diesel into the intake manifold or port. The port system is preferred as is quick warm-up, best acceleration, power and economy. This we will come to this in the next lecture when we study petrol. When we come to diesel, you will understand this then. Now, coming back to the ECM, computerized control system. ECM is a computerized control system having 8/16/32 bits. Now, these are the various electronic bits placed at various places. The more the number of bits, the costlier will be the car, actually. Mercedes and all will have 32 bits for input supply to the computer. Electric pump supplies. Now, the diagram is in the next chart. We understand it here and I'll explain you on the diagram. Electric pump supplies fuel under constant pressure to injectors. This is just the concept. Electric pump supplies fuel under constant pressure, and it's a very high pressure. Excess fuel to the tank, whatever fuel, which bypass valve, bypass is there, and the excess fuel, whatever is required by the injector, the rest it rejects, and we can't waste the fuel. It goes back by the regulator, preventing the vapor lock. Otherwise, if it continues staying, the vapor lock may occur. Excess fuel is sent back to the fuel tank by regulator, preventing vapor lock. Injector is held close by springs. We'll see the working of the injector in the coming lectures. There is a spring inside, and against the spring is pressed. When the pressure increases and the fuel is sprayed, the petrol is sprayed. Injector held close by springs, opened by solenoids, energized by signal from ECU. The signal comes from the electronic control unit. This is electronic control unit. Signal comes and the solenoid which is there inside the injector, that is operated, and depending upon the strength of the signal, the solenoid opens it to that extent to which the extent the petrol is required by the engine, depending on the load. So what is the ECU? Come to a new term, electronic control unit. The purpose is to supply power to the solenoids for opening and passing of fuel. The electronic control unit is a small pre-programmed analog computer that translates the sensor signals into command signals. You just understand that a command signal goes to the solenoid, strength of signals to control the open time of injectors, as I just mentioned, depending on the engine power required. More power required, the opening will be more petrol will be injected. Sensors control open time of injectors depending on the engine power. Sensors are placed various points. We'll study in the next page, and the various sensors gives the input to the ECU, and from there the final signal is sent to the solenoid in the injectors, and the fuel supply is controlled. Sensors positioned at various critical locations. Now, what are those critical locations where sensors are positioned? We'll see this on the chart. The working of this will be seen on the chart. Don't worry. Just understand this. Example, the airflow sensor at just after the air cleaner, which sucks the air, and after that there's at the outlet of the air cleaner, you will have sensor. Manifold pressure at the inlet of the manifold pressure and temperature sensor. It will sense the pressure and temperature and send the signal to the ECU. Throttle position center. There is a throttle position, near throttle there is a sensor, which the position which is more open or is it closed, less closed. So that signal has to go so that the ECU comments that and takes into consideration. Coolant temperature sensor near the radiator. Vehicle speed sensor, this is at the wheels. Battery voltage sensor at the battery. The amount of current also has to be controlled. So now we come to the multi-point fuel injection, and as I said, we'll see the charts which I just explained, the practical charts. Single and multi-point fuel injection. Now, let us see the single and multi-point fuel injection for petrol engines. Independent injection for each cylinder at inlet port. This is the diagram. This is the engine cylinder. One cylinder is shown. Induction manifold for the fuel air. This is the injectors placed, single and multi-point. Now, if the injector, this is a butterfly valve, as you know. Now, if it is placed before the butterfly valve, it is called a single indirect single point injection system for entire engine cylinders. There is only one butterfly valve for all cylinders. Suppose there are 3 cylinders like in Maruti. So this manifold will bifurcate from here. This is for one cylinder, another cylinder, third cylinder. So before the butterfly valve, it is called indirect single point injection. Now, if it is placed after the butterfly valve, it is called indirect multi-point injection, IMPI. For each cylinder, there will be one. And if this is indirect multi-point. So, multi-point means for each cylinder, there will be one. And if it's placed directly next to the inlet valve on the cylinder head, it is called direct. So, indirect becomes direct multi-point injection for each cylinder. Direct multi-point. There's a twist here. Injector is here. So these are three possible positions. Indirect, single point, indirect multi-point, direct multi-point. So these both are for each cylinder. This is here you require only one injector, like in the case of carburetor. Improved mixture preparation, independent injection for each cylinder at needed point. Improved mixture preparation and distribution of air supply controlled by the throttle valve body and butterfly valve. There is improvement over petrol, over the carburetor system, fitted in the intake system. Note, in single point injection, a single injector for entire cylinder is mounted, as I mentioned. I'm just reading it, I've already stated, is mounted above the throttle butterfly valve like a carburetor system. In multi-point injection, when independent injector is placed above or below the throttle valve, it is called indirect multi-point injection. Okay. Third, when injectors are placed directly into combustion chamber, it is called direct MPFI. Mechanically operated MPFI is shown in the figure. Let's read it, then I'll explain to you, or I'll explain the figure first. Operation of a mechanically operated petrol injection system. This is fuel tank. We'll start the fuel tank. The filter, the electric pressure pump draws fuel from the fuel tank through a filter. It goes to the relief valve. The purpose of the relief valve is to send fuel at a constant pressure of about 0.7 bar. Any excess fuel after maintaining this pressure is returned back to the fuel tank. From here, it goes to the metering distributor. This is mechanical in nature. No electronics so far in this. And from here, it goes to other injectors. And this is also controlled by the timing, as per the timing of the vehicle engine. So here there are 4 cylinders shown, 3 to other and 1. Let's see one. The fuel comes here, comes to the injector, and this is the air filter, manifold. This is the manifold, it comes here. This is the butterfly valve, as we have already studied, and here from here it goes. This is the mechanical petrol injection system. What happens in the electronic control system? Here, the metering distributor has been replaced by the electronic control system unit. These are the sensor signals I mentioned, placed at various points in the car. I just named them. The signal is coming from each of those points. It is the computer inside the ECU. It analyzes it and gives a final output signal. Considering all the inputs, the final output is sent to the solenoid of the injector, which operates the injector valve and so gives a supply of petrol spray through the injector nozzle. Rest of the same, fuel tank through the filter. There is electric pump drawing through the filter. Fuel pressure regulator. This regulates the pressure of the fuel. Here the pressure is much higher than in this case. And the excess fuel is sent back. Here it goes to the injector. And depending on the signal provides the output signal of the ECU, operates the solenoid. Here the air inlet manifold for air. This is the throttle valve and the inlet valve to the engine cylinder. Very simple. Nothing very technically complicated about this. So the difference is that the metering distributor has been replaced by electronics, the electronic control unit, and their signals, sensor signals all over the various points of the car engine, various places. Mechanically operated MPFI shown in the figure, this one which I explained. Relief valve maintains constant pressure, as I mentioned, this relief valve maintains constant. This relief valve contains constant pressure of 0.7 bar, sending the balance back to the fuel tank. Metering distributor supplies fuel in turn to injectors. Metering distributor, the timing is controlled as per the timing of the engine cylinders. Injector held closed by spring. Injector is held closed by spring, opened by fuel pressure to deliver atomized spray. Atomized spray then mixes with the air and gives the air fuel mixture, petrol air mixture inside the combustion chamber, and further to power the engine and power the vehicle. So we've covered these two topics. Next, when we come to lecture 10, we've studied the petrol part, we'll study the diesel part, diesel injection systems, and what are the latest developments in that. This I've explained, there is no notes, but this is very simple, so that's why I've not given any notes for this. It's just that this is replaced by this, and this is the signal, output signal, rest is the same. This comes, you can easily draw this diagram. Okay, thank you.